Okay, never mind. Okay. Okay, perfect.
Why is it plus in the...
Why isn't what?
Why did you write the plus in the sign function?
The plus, I want to emphasize that all the charge is positive because the sinus is positive. And this term is also positive. So we're talking only about charge that repel electric field, shooting it out. So, and we talked about also the strength of the charge. The strength of the charge is here the charge really weak. Here's the charge really weak. You with me? She's in charge of the zoom, okay? Yes. So you need to head to the camera, not to me. Not to the camera, to me. We're helping the Zoom people. You are actually have the privilege to see us on YouTube, so you have a better quality video. Yes, and down with that, you right now going to be in charge of the Zoom, okay? Because you see the TV better than your position. Okay, so next time we're going to have a good one. Okay, if you want, don't worry. So here I want also to talk about the science about how the charge behaves. We see that here the charge is the strongest, right? A theta equal pi over 2, right? This one. The strongest are actually distributed around this. And it's become weaker and weaker and weaker. This is really weak. And here you have zero charge. And this is the point. This is pi.
Why is that line pi over 2?
What?
Why is that line pi over 2?
Because how you define theta? Theta is starting from Z position. And then I start to open the angle. This is pi over 2. And this is pi. Okay, I think about it as a sniper with standing here.
And you don't start from the y-axis?
No, you actually start from above.
You start from the position where you asked to calculate the electric field?
Okay, in general, when we're talking about sphere coordinate, that's the convention. The convention is that you have theta and you have phi. Theta said how much I'm pointing upward or downward, and phi actually said, where do I want to shoot? At the enemy or on us? Phi live on xy. It's for the xy. It's xy.
Yeah, I know, but
it starts from x. Agreed. It's opposite when you're talking about 2D, right? Yeah. You have theta here. Yeah. Agreed? It's a mess. But this is the convention. Sometimes the convention is not that nice. You know why your keyboard actually designed that way? Why it's not A, B, C, D, E, F, G? Why? You thought about it for once? Let me tell you why it's happening. Because the typer was so fast that the machine was like this long arms that hit the letters on the paper was so fast that what happened before this one could come out, this one stuck. So engineers and scientists sit down and thought, how we can slow them down? And they said, I know, let's make the probability of letters that's gonna do the typer as slow as you can, the weakest fingers, let's do it. They did it, solve the problem. But technology changed, stuff changed, and right now we're stuck with this keyboard that slow us the most. And they'll try to do a new keyboard which is gonna make us fast, and nobody wants to buy it. Everybody's so used to this dumb thing, okay? So convention sometimes take a step, okay? But I agree that it's different than the case of 2D. When you have X and Y, agreed, and this is theta, usually. Here, it's phi, okay?
So here at the XY plane,
they live at the XY.
No, but the charge is the height.
The charge is the height of the XY plane because it have the angle pi over 2. Okay? Understand till now. Okay, so I clean it a little bit because it's become messy, and we want to discuss this charge. Okay? This charge here in the sphere, So I have this particular charge over here, this one. Okay, you can draw a new sphere if you want. This charge here, and I ask, how does it affect on the charge, on the electric field here? What does it do? So it repels. Oh, that's what's happening. This one do that. And there always, if this one has some phi, right? This one actually had some angle phi. there's another charge in the other side, right? With the minus V. Agree? A middle charge. And sorry, not the minus, yeah, minus V. A minus V. And what this charge is going to do, it's going to do this thing. So I want to shoot electric field from me also. And it's going to do this thing. And what's going to happen? They're going to sum up in the direction, these two vectors, and they're going to cancel up in this direction. These one are equal. You see it? So the main goal was to understand how the electric field behaved at that point. And what we actually revealed that the electric field is not dE. It's not this one only. Sorry, it's not this one. This is dE. It's not this one. It's just in different color. Yes, because somebody from the other side, right? This is dE. Someone from the other side gonna cancel it out. This plane, right? And we're gonna stay only with what? With this, which is dEz. It's the only thing that's gonna stay out. You understand?
Which is easier to calculate than if it was in the
Definitely. Okay. This is a vector. This is 1D. This is only the Z axis. I understand from this picture.
So it's like an integral with two variables on one? That's the
3. X, Y, Z. In space. X, Y, and Z. In space. The sphere living in space. So that I can actually make it easy and look only at the contribution to dEz. So the question now is how we continue and set here dZ. That's what I want with some correction. I need some correction. But I know that this one equal to that in what direction does it?
So how do you know if we have exactly the same oracle? Like,
let's think about it. If you didn't saw it, but we have a really cool sphere today. Okay? And this sphere is actually have a LDA. You see it? The disco ball? See? Huh? Okay, I'm starting to sell this on Amazon, so I'm gonna put a link below. Joking. Okay, so what I want to say, so I want you to look at the sphere. Okay, now you're gonna close your eyes and I'm gonna do this and stop. It's the same. So this DA.
That's one point that doesn't have another problem.
This DA actually gonna have this DA on the other side. You see, you're gonna do this thing. And I can do it all along, whatever I want.
One point that doesn't have a partner, no?
What?
The point in the middle.
In this one. And where it's direct, right?
And the origin.
And what?
The origin.
The origin, there's nothing in the origin. It's a sphere. It's not a solid ball. It's a sphere, okay?
It will be relatively if it's like a positive charge and negative. If it's a negative charge.
Yes, it's going to be negative. It's going to point downward. So you're also going to have dZ, but downward. Understand? Perfect. Okay.
And then it's opposite. But
yes.
if it was also a full ball, then it would be.
It was full ball. It was different question, not sigma. It was the rho, right? And the harder question. Okay. So this is really similar to the problem that we had with the plate. It's the same. It's the same question actually.
So the idea is that the whole contribution is only in the Z direction.
Yes, and you need to find how to find it. And now comes the part which is not physics, okay? And you should have this understanding of calculus and geometry. And it's simple. It's really, really simple. You just need to watch out, okay? What we are interested when calculating dE, we're interested at the distance, right? Where is the distance? This distance. This is d. We're looking for this d. And we can come show. We're looking for this d. Okay? And I can draw out a triangle that can help me find this d. What I know the radius, right? So I can do this. Radius, and this is time. D. This is R, and this is R. You all see this triangle, right? You see it, okay? So I'm gonna contact you to what's going on here. We're trying to find the electric field from that point. At that point, we have this sphere, which is charged, and how the charge behaves that way. It's all positive, get maximum at theta equal to pi over 2, and got again 0 at pi. To accumulate charge until here, and then it's dying out. We understand that all the charge is pointing outwards, all the dq pointing outwards, and that gives us this dE from each charge. But if you look at two charge, here you have this here, two charge, one over here and one at the other side, they're going to cancel out this thing, and they're going to sum up this thing, okay? So right now, we don't want to solve this. This is going to be pain in the ass, okay? But we do want to solve it in an easier form. We understand that the electric field is going to act only from contribution at the z-axis. The x and y are going to die out, okay? So we want to find it. So we know that we want to find dz, okay? Sorry, dE. And we need to put here some correction, okay? Let's see correction. Some correction function. We're going to make it actually dz, okay? dez. That's a general idea. I'm moving to this board. Camera people, follow me. Okay? Let's do it. Okay, we have E, the electric field, which we don't know, but we know it's building from dE, right? Okay? And we want to make this dE actually dz, because we understand that only this thing actually counts. Okay? What is dE? Let's remember, what is dE? It's, guys, it's your time. What is dE? dk, good. dq, good. What else?
The magnitude of the vector.
Yes, this square and the direction, right? This is what we have, okay?
It's only one charge?
Huh?
One charge?
It's dE. It's one. It's a dq. And we sum up right now the dq's. We're gonna change it, okay? So we need to find this d, and we also know that what really matters is this thing, right? If this is dE, this, let's call this angle is actually what? This angle is actually theta, right? To show where is the specific charge. The charge is a function of what? Theta, right? Phi and theta. Agree. Phi and theta. Okay? Phi and theta. This is the charge, where it's located, right? And also d is a function of phi and, right? Where it's located. Because this one have a different distance. And this one have a different distance. Agree? Perfect. Okay, so if this angle is theta, and this is al, and this is al, let's draw it big. D, theta, right? Al and al. I can say that this is alpha, right? Agree? This is alpha. And what's the value of alpha? Alpha equal to 180 degrees minus theta divided by 2, right? Agreed? Because the sum of all angles, these two alpha plus theta, actually equal to 180 degrees, which you have in a triangle, right? So I know this alpha. Alpha is, I just define it alpha. Why I define alpha? Because I have here alpha. And then I know the connection between dE and dz. What the connection is? This is dE, right? And here I need to put some correction, which is sinus, right? It's sinus alpha. Wait. I just want to be sure. Sinus, yeah. Why put your cosine? Oh, wait a second. Sorry, this is not alpha. This is alpha, okay? Are you with me? I had a mistake. Something was looked wrong. So this one is cosines alpha, okay? I'm cleaning this. I want you to see that.
It's supposed to be the
This is dE. This one is dE at the z direction only. And the direction is now for sure z. You see what we did over there? Just putting this thing here. And we can look only at the dz and not at the dE direction, which is really complicated. Okay? Because this thing that we had before was pain in the S. Okay? So we actually get rid of it.
Ron,
Yes.
what will be the value of this cosine? Because we just define the angle and we.
What's going to be the value of the cosines?
Yeah.
Okay, let's see how. Cosines is actually equal to alpha, and we just declare what is alpha, right? We said that alpha equal to what?
180 minus theta.
180 minus theta over 2, right? Degrees.
It's basically sine of theta over 2.
Perfect. It's sine. It's equal to, if you're gonna organize it, it's actually sinus theta over 2. Okay? That's good. Simpler. Agreed. Okay? Perfect. Okay, so right now we still fucked up. Why? Because we don't know this D, right? So how we can find this D? We have this triangle, this one, the green one, and we can find it out from that triangle. There's so many methods to do it, okay? It's up to you what is preferable to you. I use the sinus sentence, which said that each angle that I have, the length that I see in front of me equal to the rest. So sinus alpha actually equal to R. So we actually can get D out of the equation. D, and we know this, right? This one is, and we can put that inside and have another connection, right? This is cosine of theta over 2, right? We can jump between them. They're connected to each other. Each one define the other. You see it? Yes, perfectly. So we get D is actually equal to 2R sinus theta. And when this theta over 2. And then where this 2R actually came out of, I use that one. And use it as I use a sinus theta equal to 2 sinus theta over 2 cosines theta over 2, because I want to get rid of these cosines. That's the trick that I did. This is not relevant to physics, agree? This is the background, okay? I know it's sometimes hard, but that's the challenge that comes with the homework. It's not relevant to the tutorial or the lecture, okay?
If we have something like that on the exam, it's better.
Promise you that the exam is going to be easier because we don't have the time to ask really hard questions, okay? Really hard math questions, okay? But you should be smarter than us, okay? You should see, okay, I need this stuff. Let's write it down for me. So I'm going to have at the exam. You have a paper sheet, right? Start to write down what you need for the exam. Good?
So we found the D. And
we found D. Actually, we found almost everything. Let's clean the board. Let's clean the board and see what we actually have. Okay? Now we see that E equal to what? To K dq. What is dq?
dq is dA times.
Perfect. Okay, so it's actually dq is, and what is dA?
It's radius d theta and radius sine theta, sine phi d phi.
Perfect. Let's remind you that because I think this is the hardest, right? This is the hardest. You following the camera?
Yeah.
Yes.
Yes.
Ben, wake up! Everybody, count on you. Okay. So where comes this dA? You see this area? You see it? We want to calculate this area. We know that this length is actually r d theta, right? We know it for sure. It's r d theta. And this thing, what is it? Let's see the shadow. You can see in the shadow what is distance. What is this distance? It's not r, it's some shadow of r. You see, this is r.
Yeah.
This is its shadow. Shadow doesn't mean it's the same length. So this is a shadow r, shadow of the real r, dt, dphi. Let's find this shadow. This,
what you're drawing now is on the shed?
no, it's inside.
Inside.
It's
What's
inside.
the point of drawing it inside?
Just
Because you can, so you can see this distance from the middle.
Okay.
Okay, so what is this length? And what is this shadow? Is actually, as we said before, if this is phi, right? You can find from this triangle, this triangle, you can find that this is, are you sure it's phi? Let's be sure. Yeah, I think also, but I just want to be sure. No, I think it's theta. It's not phi. Because you use actually this triangle also to find it.
Yeah, because like in Calc 2, we have
This is actually, you see that this is the same as the shadow. You see it? This thing is the same. So we actually have here theta. Sorry for that. Okay? It's good to be wrong. Why?
No, because like in Calc 2, we have a different notation.
I agree, the different notation. But it's good to be wrong. Why? Because now you're going to be more careful about it.
Right.
Okay? So it's good to be wrong. Don't be afraid of being wrong. This is the best advice I can give you in the academy. Okay?
So it's
Don't be afraid to be wrong. It's important. Huh?
Sinus theta dv.
Yes, it's r d theta, so it's r squared actually. Sinus theta, d theta, d phi. This is A. Horrible A, dA. Agree. Horrible A.
The alpha star in
Al star from this triangle. This one, this is this. Okay, it's the same. It's the same. It's a little confusing, but it's similar. It's not the same triangle. It's not the same triangle. It's similar one. I'm gonna draw it here. This is the real R. This is the This is the shadow R, right? The same as here. So this is theta, and you can find, and this is 90 degrees. So you can find from this triangle. It's belong to the previous subject, okay? You should cover that. You have it in the tutorial, fully explained, okay? Go back and see it, okay? Because I don't want to waste too much time. Huh?
Why dv?
It's because of the radian, because this is a small movement with the angle dθ, okay? So we found this one. It's r squared.
Somebody has a question.
Just in a second. Theta, d theta, d phi. Yes, what is the question? Okay, hi Toby. Toby asked us that the Jacobian of the spherical coordinate is not that horrible. Okay, so this is a matter of opinion, okay? So there's a way to do it with Jacobians, agree, which apply to every system, but personally, I found it a little bit not that well understood by students. So I like to do it, you know, step by geometry and space, but definitely your question, your answer is better than mine, okay? I couldn't put it better, okay? So we have this dq, we know d, what is d? 2r sinus theta over 2. Yes, don't forget that we have this integral, and we actually now have two integrals. The phi, the theta, as we expected, okay? So 0 till pi, which is theta, and 0 till 2 pi, which is phi. Around the world, around, right? 0 till 2 pi. Perfect. So there's nothing here in phi. So we actually have these 2 pi outside, and we start with this thing, which is k outside, r squared outside, sigma 0. Nobody told me about it, but we are missing sigma 0 outside, and we are actually missing all the sigma, right? We have also sinus theta, right? Wake up, wake up. Okay, so we have this sinus theta, which is horrible. We have here sinus theta, and I'm about to faint out when I see this stuff. The theta 0 till pi. Yes, and this one cancel with this one, right? So this actually, this one actually died, so we can get rid of that. And sorry, this one was squared, right?
Yeah.
Oh my God, this is horrible. This is where this one actually contributed to us 2 over here, right? But it's killing this r squared, right? Yeah. Because this one. So you need to solve that thing. Now you need to solve this integral. And it's not relevant to the class, okay? you can solve it. This one actually equal to, I honestly put it in a calculator. Just the camera follow me. The camera follow me. Camera follow me. I'm gonna walk slowly. Okay, good. So this integral actually equal to 8/3. And the question is done. Okay? No, you can. This one also cancel out with this. You have only this. Okay? This.
Theta over 2, right?
Yes, this one is, I'm missing 1/2. Theta over 2.
Theta over 2.
Where is the theta? This one.
Like the cosine. Yeah.
Cosine theta over 2. Okay, also.
No,
here.
this is sine. That's the sine theta over 2.
Theta over 2, which is this term.
But it will just cancel once.
Right? So agreed, it's a really hard question, but not in the physics, in the math. So I cannot help you with the homework, with the math. This is your own challenge, okay? So this is the.
We didn't have so
Huh? I agree. It's really paining. It's a really. I think it's a really pain in the ass. I agree with you. The math here, I think it's redundant, but the concept were super crucial. You cannot be. I want you to be confident about the concept. The concept gonna be at the exam as well, not the math, but the concept gonna be on the exam. Math, we save it to the homework. There's also important to let you practice at these ideas. Okay? Perfect.
Did you have another way of solving it without geometry or no?
What?
The question without geometry.
If you're gonna think about something, let me know. That's how I did it. It's the best way, best to my understanding. Okay? Cool guys? Camera following me, camera following me. I'm going back to this board and I'm gonna clean this one up. Okay? So right now, we're gonna move to the next concept, which is Gauss's law. Okay? We remember Gauss's. Can you stop the video and we're gonna do a new one? Press and press again. Never mind. Yes, we got it. So guys, right now we're gonna do a question regarding Gauss's law. And somebody remind me what is Gauss's law is?
The surface integral.
It's
the flux.
And the flux, perfect. And how you write the flux? It's integral. Surface integral, which means we have some envelope, right? We have some envelope. E, the vector, dot dA.
Is
Equal to the charge inside. In, I love to say in A. In A, by some constant, right? Okay, perfect. So, to all of you that already feel comfortable with Coulomb's law, I want to tell you that Gauss's law is actually a better way to find electric field. This is the easy way to find electric field. I know that you saw tutorial 3 and you feel a little bit, dude, I don't know, it was a little bit complicated, a lot of equation, a lot of to imagine stuff. I know. At the beginning, it's, I think, the hardest subject of the class. Confusing, agree. But we're gonna see it's always the same. It's always repeating on itself. And I do it really rigorously, step by step. But you see, eventually, you're gonna jump to the final solution because you will be so familiar with the method of Gauss. So eventually, I'm gonna tell you some piece from the future. You, in 2 months from now, are gonna say, I would never choose Coulomb's law against Gauss' law. I will always choose Gauss' law. It's easy. Okay? Gauss's law make our life easy. How I remember what Gauss is all about? What is the first letter of Gauss? G. And I think about it as geometry. First, I need to deal with the geometry. And what's the last letter of Gauss? S. And I think about the sum of charge. Okay? So that's what I want you to think when you're dealing with Gauss. That's what I have on the left, that's what I have on the right, okay? And this thing is actually the area that I'm choosing is not real. It's something inside our mind, okay, that we decide. We can choose the thing that is easy Easiest for us, the most, okay? So in the tutorial, you saw that I chose a rectangular, right? And it was not real. The real thing was the submarine. The submarine in the question was real. Okay? So let's continue and I'm going to show you the problem. The problem is you have this wall. Can you follow me?
What is your Q in A?
Q in A means what is the charge inside the imaginary area. Okay? You see tutorial 3? So tutorial 3, so this question is going to be a little bit problematic to you. I'm going to put right now a link to tutorial 3 if you didn't saw it, but here in this box, an imaginary box, there's no box here, okay? Imaginary place, follow up, so hold on with your questions because I don't want to hinder the rest of the class, but after you're going to saw it, you can revisit this video, okay? So we have in space some x, y, z, x, sorry, I don't want to do this question yet. I want to do other question, which is easiest. Do you remember how to calculate the charge from a wire, infinite wire? You did it by Coulomb law, right? After you did it by Coulomb law, you wanted a little bit to die, right? Yeah. A little bit, you needed to change angle. It was this, okay, let's say I'm here from the charge, let's divide it to dq. Okay, the charge is infinite, so it's the boundary layers are here, and I don't know how to talk about dl, so let's change it to theta, this angle theta, so it was super complicated to do it by Coulomb's law. I want to show you how simple it is, Gauss law, and the reason I changed questions because I want the people that didn't see tutorial 3 to have a little bit paper. So see how easy Gauss's law. If I see some infinite wire, okay, when you see the word infinite, okay, this is a clue. Use Gauss law. Okay, this is a clue. It's not always hold, but usually it's helping us. Why? Because you're gonna have awesome geometry, awesome symmetry. So we have here symmetry of what? A wire is actually what? It's a cylinder, but really with the small radius, agree? So the first step in Gauss is to decide, to understand, the first thing to understand is what is in general the direction of the electric field. We know that this point gonna do electric field in this direction, right? And also in this direction, each point gonna do this, each charge. But we know, right, from symmetry, that we know that if I have here a point and here a point, so what's going to happen? The same thing. This one going to push in that direction. This one going to push in that direction. They're going to stand up here, right? Yeah. You understand this concept? It's similar to the sphere, but on a wire, right? If we have here positive charge, that's what's going to happen. And this happening all degrees, right? In each direction. So actually, the electric field, I don't know its size. I don't know, but I know its direction for sure. It's radially pointing out from the wire, agree? And of course, it's related to the distance, right? I don't know how it's behaved, but I know the size is a function of the distance, how far I am from the electric field, from the wire, the producer of the electric field. This one agreed? If you know this thing, Gauss is probably gonna kill it, smash it, okay? The reason is because you know something about the geometry, about the symmetry. You use the infinite idea. What the infinite idea said? It said that no matter where you're gonna put charge, you're gonna be equivalent charge on the other side, you're gonna promise you that. That's the idea of infinite wire, right? Let's say I'm gonna find it. There's infinite options, right? One of them gonna do it. Okay, so let's go back. So if I understand how the electric field is behaving, I'm going to choose some area. Which area I'm going to choose? Someone that is actually really helpful, right? What is this?
Dot product.
Dot product. Dot product is that I think as a dot product is die vector, okay? Dot product is actually killing vectors. That's what it's doing, right? You make this one to be the size of it, this one to be the size of it, and cosine is the angle between them. That's what he's doing. You just killed the vector, okay? Dot d sine die, okay? Die vector. In Hebrew, die, it means stop. Okay, stop vectors. Okay, that's what this thing is doing. Okay, perfect. So I need to choose something that's gonna give me nice angle. Which angles we love the most for cosines?
0.
Angles?
Oh,
Pi over 2, which give us 0. So agree. Alpha equal pi over 2. Mwah. Perfect. Okay. What is the second one we also love? 0 alpha equals 0, which means it's equal to 1. And here it's 0. So this thing actually kill the integral. Kill it, smash it, you don't see it. And this one actually said, forget about the vectors, dude. No vectors in this game. Easy, easy, only size. So that's the idea. So when you need to think about imaginary A, that's what you're gonna do. You're gonna see this is the A. You need to think about some envelope that's gonna give you this thing. How are you gonna know it? I'm gonna give you hint. If you see something, you know the term eye under eye? You know it? Teeth under teeth, tachat. Here, okay. So if you know the term is said that if someone do to you something, you're gonna do the same thing back.
tit for tat.
What?
It's called tit for tat.
How is it?
Tit for tat.
Tit for tat?
Yeah.
Nobody said it. Okay. Okay, never mind. But if you know some sentence, so use it. Okay, you tell me after the class. Okay, I want to use it. Okay. So if this is kind of a cylinder, what area I gonna choose? A cylinder. Okay. So this is a little hint how to use Gauss's law. Okay. If it's a cylinder, I want to use its benefits, its geometry, and apply it. So if I'm gonna do cylinder, this cylinder is real or inside my head? Inside my head, I'm crazy. I see cylinders everywhere. Okay, this is the cylinder. And this cylinder has some DAs, right? These ones, DAs, DA, right? It's like, okay, if I would choose this one, you see the DAs? And I want you to notice something. The DAs is a magnitude or it's a vector? It's a vector. So it's really weird, but this DA have some direction. It's pointing somewhere, okay? The convention is the DA pointing outward. Easy way to think about that is think about that as if the DA actually have a face and have a normal, which is a nose. That's how I think about it, okay? So for me, each DA is a smiley. So this smiley pointing in that direction, and this smiley pointing in that direction, and this smiley pointing in that direction. Sorry, not here, but actually here. You see it?
Yeah.
You see this DA? You see the smiles? Another analogy to think about is to take a flag and put it in the ground. This is the DA. Another analogy. What suits you best? Okay? Perfect. Something that must happen is if you choose imaginary geometry for Gauss's law, it must be closed. We do close in math by doing just close circle, which means this is a close, this is end, okay? I love to do this here, okay? So you can remember it's a 3D, okay? It's a 3D and we look at the envelope, okay? What is an open space? Perfect, this is an open imaginary thing. You see this opening here? If we're gonna fill it with water and they're gonna pour out, right? But if you're gonna choose a closed cylinder, will they pour out? No, it's a closed cylinder. So the way to think about if it's a closed area or open area is if you're gonna fill it with water, you're gonna have a way out, okay? So a cylinder is appropriate for Gauss's law. Agree? Understand? Perfect. So right now, yeah.
I know that we got a cylinder because the wire is in the shape of a cylinder, but is that like even wires are like this? Because in my head, it's like an infinite, like small wire as well.
Every wire within the slit, honestly, every wire you see, it's a cylinder with small radius. Every wire. Right now, I'm looking at the tree. I see this branch, okay? It's kind of a wire. I look at the electricity. It's a wire. Agree that it's not a perfect wire, but nothing in life is perfect. This is not a perfect circle. This is not a perfect circle. If you zoom in, this is not a solid line. If you're gonna zoom in, you're gonna find out that I lied to you. But in real life, you are engineers and scientists. The idea of you is to find the simple way to get to the solution. I know it's not a solid line, but if it's a solid line, I can do that, that, and that, and that. How much it's true what I'm saying? To this amount, which is fair, it's good enough, okay? No matter what you're gonna do, okay? If, I don't know, I'm standing on a weight machine, right? To see how much I weigh, and the day after I cut my hair. It's not the same weight, but it depends what you're looking for. But for me, if I gain weight, lost weight, it's not that relevant. It's gonna be okay with there, without there, the same thing happened here. I'm gonna be okay if we're gonna say it's cylinder, and this is your choice, your way to choose.
You can take it as a cuboid too, like about.
What?
You can take the imaginary.
You can do the box, but the question gonna be, is that gonna be beneficial to you? That's a question. Okay.
It will be similar though, right? For example, like if the
let's see why I choose cylinder. Okay. Okay. You saw it actually in the tutorial, but we're gonna do it the simple way. So I got this method. I have a cylinder. We have this DA. I want to ask you stuff. Okay. Let's deal with this integral. Okay. Let's finally kill it. Okay. Let's see what this integral is all about. If it's an integral, we know that we can take summation and start to cut it, right? 1, 2, 3, 4, right? 4 is equal to 1 plus 1 plus 1 plus 1. The same thing with the integral. I can take this integral, right? And I can open it, the integral of the area, which two different area that I had.
circular faces and
I have this area, right? The sides. And I also have this one, which is the body, right? So we can say that we have this one, right? We have this. How many we have of this?
2.
We have 2 of these. Let's not do the 2. Let's just draw 2. We have 2 of these. DA. And we also have this thing, right? And if this one is in length L, right? Okay, so let's do not L, H. Okay, height. So this thing is actually, this one is H, and what is this? Is this circumference, right? 2 pi r, right? H 2 pi r. This is the size of this thing. E, dA. Let's draw it, okay, because I see some crooked face in the audience. This one is H, right? This one. If we're gonna take this cylinder, perfect example, and I'm gonna cut it, what do I have? Rectangular, right? And what is this line? What is the length of this? Sorry, it's this way. Okay, cylinder. Open. Exactly. Thank you. 5 points. Okay, so this is 2 pi r. Okay, the radius of this cylinder. This radius is real? Yes, beside my head. Nowhere else. Okay, so these are. Okay, now I want to talk about this node. Okay, we studied the electric field pointing where? Radially out. This way, right? This way, this way, this way. Agreed? So what's going on here?
0 degrees.
This is E, and this is the A. Agreed? What is the angle between them? Pi over 2, which said that the cosines. So I know that we have here electric field, crazy electric field, with so many different distances, so many. But they're gonna die out because every time DA is gonna say, I'm going that way, and the electric field said, I'm going that way. And what's gonna happen here? The DA is gonna point that way, the electric field is gonna point that way, or that way. It's gonna be 90 degrees each time. So they're gonna die out, okay? Perfect. Now we stay with that. And if the electric field is pointing that way, and DA pointing that way, the angle between them is?
0.
0, we have that case. Agreed? So what's happened to this? It's become got rid of the vectors, not the dot product, the vectors. Okay? Now it's a magnitude. And I want to ask you a question. This is many different distances, or it's one distance? It's specific capital R, capital imaginary R. Okay?
What is the small r?
Huh?
What is the small r?
This, why this is smaller? Because you have this electric field, this one, and the far away, and here, this one, this one, this one, this one.
Okay. The small r is the distance.
Woo, so many. But here you have only one.
Capital log is like the function of the length of the wire, right?
Again?
The capital R there, that is the function of the length of the wire.
Ah, you mean that?
The whole, yeah.
Yes. So this is R, is actually making this thing, 2 pi R. You see? Okay?
So this is times cosine 0, which is 1.
Here, you have cosinus alpha, which equal to 1, and this is sine. Okay, so if this is a constant, and the dA is not running on A, right? On R. It's not a function of R, dA. dA here, and dA here, and dA here, and they all have R, right? They're on the envelope, right? If this is the cylinder, they are around the envelope, right? They have the same radius R. This is dA, right? This is dA. They all have the same R, right? Perfect. Smile every time I put something.
Yeah, because you like a magician.
Yes. Okay, that's me. Okay, so so this dA not depend on R, and this is a constant can go out. ER is on the side. It's a magnitude. Life is the best. Okay, but what we still have here, integral that ask if you're gonna sum all the dA, what you're gonna get?
2 pi R times H.
Exactly, you're gonna get a total, the area of this part. Because you're gonna sum this small thing, this small thing, this small thing, this small thing, this, right? Every dA, every square. If you wanna sum all the square of this sphere, what you're gonna get eventually, the area of a sphere. So
What is the one you put on the dA?
here, I just want to say it's not a function of R, not a function of R. It's the same. You get the same value for R. Okay, perfect. No, don't say it like this. I want to say it's not a function of R. It's not as smart to put it in that way. Okay, so we have this one out. This one we know it's equal to 2 pi R multiplied by H, right? We just found this part, okay? And I'm gonna tell you, in a few days, in a few weeks, after a lot of problems, you're gonna do it. Cylinder, die, this one, done. It's gonna be like 10 seconds. And you're gonna jump to this notion.
I think we did it also with Michal.
Perfect, okay? Perfect, okay? You're gonna do it? And I do the same thing we did with Michal, but give you like a little perspective how I see it, you know, with this stuff, with dA, with the nose, with G and S, you know, it's my interpretation. Okay, how to, I think it's not enough to tell you how stuff it is. It's to give you tools to remember, to use it, to have it, right? It's different to understand than to know it, right? It's two different things. That's the idea what I do here, okay? So we found that. Now the question is, what is this guy, okay? So somebody can explain to me what does Q in A said?
It's the total charge on the wire.
Total charge, not on the wire.
Within the wire.
Not within the wire. It's not perfect. You're correct, but it's not perfect. Okay, what's the name imply? Q?
In A.
Which means you're taking into account all the charge inside the area you just did inside your head. If there's a charge on the wire, sum it up. If you have a charge flying by around here, you need to sum it up. If you have a charge here or here or here, then that didn't count. If they're not inside A. Agree? Agreed? Understood? Perfect. Okay. So, what is this charge? Lambda multiplied by H. Done. Done. Finished. And what Gauss's law said? Geometry equal to sum of charge.
Because it's a wire, it's not there.
What?
Because it's a wire.
It's a wire. The charge is only here.
But we calculated A as a cylinder, no?
A is the cylinder. So
It's just the length we.
A is inside my head. It's not real. It's not, I'm crazy.
If there are charges that are in A that are not on the wire.
So, but there's side A. If there's side A, they should come and be here in the equation. That's what the equation said.
So how is it lambda H?
I'm giving you that the wire has charge density of lambda.
Yeah.
Okay? Charge density. So if I put here, let's say some axis, I need to sum up all the charge inside the cylinder, right? If this length is h, right? This length is h. So the charge inside is lambda 0 multiplied by h. This is a constant charge distribution. Right?
But what inside? What not on the line inside A?
This part of the wire is inside A.
Yeah.
So this is a charge that's inside A. There's also charge here, but they're not gonna count it. And if there's here some cool charge, let's do a cool charge. Hey, I'm a cool charge. I'm doing my business. I do whatever I want, but I'm outside the party. I'm not inside A. This one is outside the party. That's one having good time. Okay? Understood?
Inside A, there must not be any other charges than on the wire.
In this specific example, yes. There's only charge on the wire, but the concept is the charge in A. Please put here A, in A, not only in. Okay? Perfect. So let's do calculation. E is a function of R, 2 pi R multiplied by H equal to lambda 0h divided by epsilon 0, right? You have this. H dying out. What does it say that H dying out?
We don't need the length of the.
My imaginary cylinder could be in every height that I want. Could be that, whatever I want. Doesn't matter. This is your freedom in imaginary, imagine things relevant to the question. Okay? And so ER equal to lambda 0, epsilon 0, 2 pi R. Right? I divided by this thing. So 1 over R, lambda 0, another way to orient it, 2 pi. This is the final result. Okay? And I promise you, this one took 10 seconds. I agree that this one was a lot because we talked about it. But after you see, wire, I know what to do with the wire. A box, okay, I know what to do with the box. Sphere, I know what to do with the sphere. Pretty much all we have in this class. It's going to be the same every time. It's going to be your favorite, okay? Yes, question then.
Gauss law holds up only for uniform charge distribution or no? Because we took the ER out only because it's uniform charge distribution.
Again.
If the distribution wasn't uniform.
It was like crazy. We said
Yeah,
we had a lot. So
Yeah.
it doesn't matter how it's distributed. You only care about the charge inside. But if the charge was oriented really weird, maybe electric field would not point in that way. And so you didn't have the symmetry. So you cannot use this cylinder maybe. Or maybe you could. It really depends. So the challenge in doing that would not got that not complicated. The complicated thing gonna be, what to use? Which area gonna do it? Okay?
But if I have like a distribution that is not uniform, but it's not like constant. When I calculate the integral, I'm gonna have to actually calculate the integral.
Yes. So this is the reason you have Coulomb's law, you have Gauss's law. Gauss's law coming in when you said symmetry, easy, nice, I know what's going on, Gauss. Oh fucking shit, what's going on here? I don't have a way out, Coulomb. Okay? That's a general idea. But in life, if I'm gonna take this thing and I'm gonna charge it, let's do it. You know what? Let's charge it. Okay, I have this thing here. Okay, and I have this. Cameraman, follow me. If I have this, okay?
Put it down.
Lift it. Hey, wait. Hello, YouTube people. I'm fixing the camera. Okay? Okay. If I'm gonna take this sphere, okay? If I'm gonna take this sphere, I'm gonna scrub it a little bit. A lot, okay? I'm gonna scrub it. What I'm actually doing, that I'm taking electrons out of it. Okay, that's what I'm doing. I'm taking electron out, and this one become positive. Okay, this is aluminum. Okay, if I'm gonna put it close, all the electrons in the aluminum would want to follow this thing. Oh my God, it's fucking moving. Okay, I didn't touch anything. Okay, that's what happened. Okay, so this thing until a few hundred years ago was like a magician show. Look at me, no touching. I do whatever I want, and it's come to me. Now they neutralize. That's what happened. Okay. Now I'm gonna electrify you. Okay, so usually in nature, what's gonna happen? The charge would not have any reason to go to here, or to go to here, or to go to here. They're just gonna distribute it evenly. Usually that's what happens. Of course, you see this crazy geometry, maybe stuff gonna change, usually at the end, okay? But if I am a small bacteria or coronavirus, and I come near to something, for me, what is it? Infinite wire, infinite cylinder, actually, right? That's what I see. So Gauss's law, camera, Gauss's law is actually super useful in real life. Thank you, Gauss, for making the math easy, okay? I know you don't believe me at the moment, but trust me, Gauss make life easy. You don't want to do what we did in the previous question every time you have something. Try to calculate this phenomena with Coulomb. You don't want to die. It's really hard. But with Gauss, it could be 2 lines. 1 line, maybe. Okay?
Epsilon is a constant.
It's a constant. It's go back to this board. So epsilon equal to 1 over 4 pi k. Right? Remember it? I have it in the book, I think.
Yeah, it's okay.
Yeah, perfect.
B for this because it just showed up randomly.
Wow.
But like it's a constant for.
It's a constant. Okay, K was a constant. A little bit history. K was a constant that found out in experiments. Okay, you have different K for different units of measurements. Okay, so okay, I have this force, but I need to fix it by this constant K. Okay, and then this thing, a lot of years later, come up, and this thing actually related to light. So I'm gonna do like tell you a secret that light is actually electric field and magnetic field dancing together in a crazy dance. Okay, that's the truth, and this is the end of the class. The end of the class is showing you that, and this is the property of light. Okay, of mediums. Okay, this is the net of vacuum in space. Okay, outside of the Earth, this one all, and if not, we need to fix it by some constant, epsilon r. Okay, but it's not relevant for now. But we can write this thing if we're gonna put k instead, as you recommend us to do. It's gonna find out to be 2k lambda over d, and d is gonna be the distance. It's gonna be r. Okay, the distance from the wire. I don't want to use r because sometimes you know r is a given thing. The sphere, the cylinder. So I always love to use as a distance d. It's more intuitive word.
It could be also diameter.
Huh? Yes, it's dependent on the field. Agreed. There's not enough letters in English. Agreed. Agreed. Okay, so right now let's do the Gauss's question I wanted to do. So I'm gonna clean this one out.
Can you do the one question about like a spherical shell, like concentric spherical shells?
Concentric, what do you mean? I did it in tutorial 3. We did like this thing, right?
Oh,
Right?
yeah.
which was the cylinder from the submarine. We did it. Revisit it, and don't worry, you're gonna have it at homework. Promise you. Okay, perfect. So you had this question in class in the homework, right? You have this was the x direction, this was the z, and somebody told you that this is the infinite wire, right? Oh, and this is the infinite wire. Oh, and this is the infinite wire. Oh, right? We had this, and I asked you what is the electric field. This is y, and here at point A, right? A, this one also A, and this one is minus A, right? So ask you what is the electric field here. Remember the question? You do? Perfect. So in this question, we can solve it using Gauss. Okay? So we know from Gauss how wire behaved, right? We know that wire behaves that way, which means it's radially pointing out, remember? At the distance d, this is going to be its value. Agreed? Right? So, I want to ask you a question. If the electric field, remember that from Coulomb law, we talked about the electric field can be used as a superposition, right? So what I want to say, the electric field here, I see a complicated task around it. I see a lot of wires, a lot of stuff, a lot of charges. But what I know that each one individually counts. So I can take this complex problem and split it to 3 easy problems. Only one wire, right? So we have E1, let's call it, EA plus E0 plus E minus A, right? That's gonna be the solution, agree? So every time you see a complex problem, just kill it. Okay? So this problem we already solved is this answer, right? So what we need to do? Just put the right D, right? And done. The question is easy. So, but what you need to be careful is the directions, right? Because this one have its own wall, its radially direction, and this one have its own radially direction, and this one have its own radially direction, right? So this one gonna give us contribution in that direction, right? And this one gonna give us contribution in that direction, right? So what's gonna happen? They're gonna hit each other in that direction. Dying out, but they're gonna sum up at the y direction, right? And this one, actually gonna say, you just wanna give you in this direction. So we already know that the 3 of the wires gonna contribute to the direction. You understand? It's always the same. First, try to understand what's going on in the problem before going to the equations, okay? Who is pushing who? The can, where should it go? Before I put this thing that you, right? Before I put it, I know what's gonna happen. That's how I want you to react. Before you calculate, I want you to know what's happening, okay? Even if you feel that you know what you need to do, okay?
So you consider it as one wire?
I'm going to do summation of 3 wires that each one of them is an antipart and filling alone is in the wall. That's what I'm going to do.
Do they contribute in that direction, but also?
I know that I need to take into account, no, this one going to contribute to this direction, for sure. They're going to push all it mighty in this direction. But this one going to say, I'm going to push mighty. All the force that I have.
But isn't it symmetric to the other side?
It's symmetric, why not? This is A, this is minus A. This is plus A. This is minus.
No, I mean, you have the y-axis, it's going to the minus y direction, then it should be symmetric in the other side, no?
I don't understand the question that you're asking.
You have the
y. Want to come to the stage?
No, it's okay.
Okay.
Like the right direction.
I can embarrass you, really good. Yes.
So you have the y direction, right?
You have y direction,
And
yes.
the chart, I don't know, right? The chart doesn't like look the same way in the other layer?
Or there shouldn't be something in the minus y direction. That's what she's asking.
Yeah.
Here? I don't care about what's going on here.
No.
I don't care. They asked me what's the electric field here. I didn't clear it? Okay,
It
sorry.
should be symmetric to the other side.
Yeah.
Yeah.
Okay.
Smart move. Yes. No, it's a smart move. If I'm gonna ask you also about here, you're gonna say, they're the same. You see the symmetry. It's okay. So this one equal to what? This distance, right? This is A, this is A, so this is A squared plus A squared, 2A squared, right? So distance. So this one is actually 2K and lambda. Wait, easy. This one is, wait, I fooled you. What is this? The almighty power of the electric field. Do I gonna use its whole power? Do I gonna use all of that? Only that, right? So we need to find some correction. So if 45 degrees, agreed. This is 45 degrees, 45 degrees. Why? Because this is 90 degrees, this is A, 45, 45, right? So we need to put a correction of cosines 45 degrees. Agreed? Okay? And now I want to ask Nomi questions. What is this value is?
What?
Nomi.
Same as that one.
This one and this one. This is the value, the contribution, this contribution, right? What's going to be the contribution of this one?
The same as that one.
Multiply by 2. Smart move?
Yes.
Save time. In the exam, this classic question, for example, by the way. This one classic question because there's no calculation here. It's really easy. No plus science inside there, what the fuck? No. Okay, it's easy. This one, value 2K lambda, the same, 2K lambda over 8. This have all its power, nobody gonna fix it, is pushing in that direction, right? Question is done. Okay, you need to clean it a little bit, sum it a little bit, but that's a question. Superposition, sum everybody. This also has some 1 over square 2, right? Because it's 45 degrees. So it's gonna kill that one. An easier solution. Okay? Yes, question.
I know that in this question we already know the electric field of which one of the wires. So that's how it's easier. But if we didn't know, can we create like one imaginary surface that includes all of them?
You could, but it was a little problem because the symmetry was really hard. Even though what I would do, what I did right now, I did the whole thing. I would look at this and said, okay, I don't know what's happening. I would start with that. I don't know what's happening, but I know that it's easiest question. I can make this question easy. Then I would solve how it behaves for general wire. Actually, I would solve this because I don't have this cosines. This is the simplest example, this one. I would solve for it with Gauss's law. Then say, now I have 3 of those. Okay? You understand the method? Okay? So agreed. When you have this thing, you don't have a symmetry, but with superposition, you can actually dumb it down. Okay? That's what we do. That's what we do with superposition. Superposition, dumb it down. Make it stupid and easy. You have 3 easy problems. Okay? This.
With the square root of 2
what?
times A, when you multiply by cosine, it gives you the y direction.
Yes, when you multiply by cosines 40 degrees. This
But
thing.
isn't it just the distance?
Okay, I drew this. This is E from the wire plus. Okay, this is 45 degrees, and this is E at the y direction, right? Who dined out this thing, which is this thing, which is E at the z of a plus, a plus, a plus. Right? We only care about this one, which is equal to the real E cosines 45 degrees. Okay, that red circle is actually that this thing is.
So it's just the E that you multiply. It's not the distance that you multiply.
No, the distance. No, the distance is actually this thing. For each one of them, they had a different distance. Okay. Understood? Next question. Final question at Gauss's law. Ready? Cameraman, please stop the video. Wait, I wanted to clean it before. You know how much time did we save right now? Because we saved 5 seconds. multiply by how many students you have in the class, multiply by every year. Okay, so 1 minute now, think about how many minutes, wasted minutes we save. Just by thinking, just by care about each other. It's crazy. Huh? Bye. Okay.
Start now.
Wait, reading this also. Naomi, it was great to have you here in class. Please come more, okay, not only Zoom.
I try.
I prefer your 3D version instead of your 2D version, okay? Okay, now you can do it. Hi everybody, we got an awesome question regarding Gauss. And what I really want to point out in this question that A, who is A? You remember? We have Gauss's law, which is the flux, right? Flux E dot dA equal to what? 2 in A, Q in A, divided, yes. And how I remember this equation? The first letter of Gauss is G. I need to take care of geometry. Don't forget this is a closed area. Closed area means if I'm gonna inject some water inside, they don't have where to go. They stuck inside. Glass is not a closed area, right? Because I can inject water and pour it out. A cube, closed cube, it is. A sphere, it is. I can inject, nothing gonna go out, right? So that's the idea. So geometry. And what is the last letter of binary? What is the last letter of Gauss's? S, which means sum of charge. To sum all the charge where? Inside this area. If I choose a sphere, inside the sphere. If I choose rectangular, inside the rectangular. Not what happened at the neighbors. And the neighbors in the other city, I don't care. I can only have the stuff inside the box. Perfect. So, to the question. The question is that I want to emphasize that this area is not real. That's the idea of the question, okay? So I have my nice space, okay? Space is divided to X, Y, and if I draw it in that direction, it must be that Z is actually pointing in that direction, okay? Right Cartesian coordinates. Okay, and I have this imaginary box. This is the imaginary box that I have. I have a box, go like this, like this, like this. Is this box is real?
No,
it's not real. This time I have it's my dA and my A and my area of this thing. I decided right now for this question that this area gonna be a box. Okay, that's what I did. Sorry. Can you close the door? Thank you. Okay, perfect. So now I also know what it's given. It's given that the electric field in space. I don't know who is the motherfucker that created this electric field. I don't know, but I know that it's equal to that. When y is smaller than a over 2, and my value is minus sigma divided by 2 epsilon naught at the y direction. And when my y is in between 3, 4a and a over 2, its value is actually minus 3 sigma 2 epsilon naught at the y direction. And when I am actually bigger than 3a4, its magnitude is sigma 2 epsilon 0 y. What you can say about this electric field?
It's variable.
It's what?
Variable. It changes.
It's changing. It's what else? It's ugly. It's not nice. But what we do know?
Points and y.
We know its directions, okay? So we know the electric field and we know its direction. So this is a little bit Gauss field. I know directions, I know the geometry, I can use Gauss. What I really want to do with Gauss, I want to have an A that I can take this dot. What is this dot is actually is? Dot is from kill vector or dot d die vector. In Hebrew, die is also stop. Die vector. That's how I see dot. Okay, so dot actually taking, if I have E dot dA vector, is equal to the size. Size of them multiplied by cosinus alpha, and alpha is the angle between these two vectors. And this is E, this is dA. What is the angle between them? Okay? That's the thing. It's killing the vector. This is a scalar, not a vector. Okay? Perfect. So they asked me wrong. Knowing that this is the electric field, what is the charge inside the cube? Only inside the cube. Can you tell me what is the charge? This is the definition of Gauss's law. Okay? Gauss's law said, take imaginary thing. Okay? If you can calculate this side, I for sure promise you, it's equal to the charge inside. I don't know what's going on inside. I don't know how crazy the party there is, what's going on, how the charge is distributed, but I can tell you for sure what is the total charge inside this imaginary box. Understood till now? Perfect. So let's solve the problem. Okay? We have E. We have E. We have A. We just need to do it, right? So if I have a box in the integral, what we said about the integral, what's really fun with summation? 4 equal to 1 plus 1 plus 1 plus 1, right? This is all. Same thing with the area. If I sum up the A's, I can open the box, right? I can divide it to some regions and solve the equation for each region, right? So I'm moving to the other side. Please follow me. Camera people, thank you. Special thank you to the people with the camera and the people that are helping me translate. Thank you so much for helping the class. So I have this integral and I have this box, okay? E dot dA. What I can do to the box, I can open it, right? Let's open it to 6 walls, right? E wall, right? We have many E walls, dA, plus we have, not 6 walls. We have 4 walls. And we have also, we have a roof and we have a floor. We have a roof and we have a floor. Do you see it? Roof and a floor. We can do it, right? It's okay. E roof, dA, plus E floor. What I really want you to notice, is you see that the closed sign of the integral? What happened when I open the integral? It's not anymore closed surface, okay? The semantic. You see it? It's not a closed. If I'm taking a box, this box is a closed area. You see it? If I'm gonna inject water, they're gonna be stuck inside. But if I'm gonna cut it, now I look at what? At the side, at the roof, at the floor. If I'm gonna put water here, it's an open, right? It's open, it's an open area. Perfect. So now what we need to do, we know E, right? Let's try to understand dA, okay? Let's observe it. Where is E heading?
Y direction.
Camera, please. Michael Jackson. Okay? Where E is heading? Only at the Y direction. Y direction every time.
No, that is ZU.
Only at Y. Also here, also here. You see it? Yeah.
That is Z, Y is up.
Sorry. Thank you. Thank you. So Y is actually pointing that way. Pointing that way, that way, that way, that way, that way, that way. You see it? dA. For that side, for the roof, where is pointing? How we do dA? Remind you, dA is taking the sphere and starting to draw smileys, right? The nose It's a known one. It shows where is dA heading. This one is here, and what is this one? This dA is in this direction, right? Okay. So I see here that the angle is 0. So I can go back, camera. So when I look at the roof, I can say that this one is actually the size E. At which location? I didn't say, but the size of the box are A by A. Okay? No. The sizes of the box are A. Okay? A by A by A. So this is E. At what location? Y equal A, right? It's only one value of electric field. Okay, Y equal A. And we have dA. And we have a cosines to be 0, which means equal 1. Sorry, 0, which means equal 1. What happened to the walls? Let's go back to the walls. Okay, I didn't draw it, but this point is, this one is the region, this one is A0, 0, this one is 0, 0, A, and this one point is, it's like A on A cubed. Okay, and this one is 0, A, 0. What's happened to the walls? Electric field, this is the box, okay? This is the box. So this is not a cube, right? It should be a cube. dA, smiley, right? Smiley. Pointing that way. And the electric field pointing that way. This one, dA, electric field, only at Y. This one, dA, electric field, pointing that way. 90 degrees. Cosines of 90 degrees is 0. Let's go back to the board. So this one is actually integral of E at many places. Crazy places. Okay? Think about the wall. The wall, you have X, Y, and Z, different location of the walls. dA, cosines, pi over 2. Dying out. We don't need it. Yes? Now, we have the floor. What's happening in the floor? It's E equal what? 0. dA. And the cosines is what?
0.
Not 0.
Wait, pi, it's pi.
It's pi. Thank you. It's pi, which means it's pi negative 1. It's not that bad, right? It's okay. Negative 1, we can deal with that. So the area that was given, the box, was make sense. Yes, we got it?
Yeah.
So what we can do with these constants? What is this dA actually? What's present? What's present? The roof. What's present the roof?
The side square.
If I have this box, let's go back to this drawing. If I have the box and I want to distribute it to many areas, what is the size of this area?
dA.
It's dA, and it consists of some contribution in dz and some contribution at dx, right?
But since like the size is A, we can just take it as like d small a.
What?
The size of the small cubes.
What are you talking about?
Like, since the side of the cube is A, so the small.
You said that all this area is equal to a square?
No, like when we take the small part of that one you took, can we just take it as d small a?
Yeah, this is dA. I just want to say, let's go there. I just want to say that this dA is actually dx multiplied by dy. That's all I want to say.
Oh,
You got me? So this one is this one. This one is the same as this one, right? And this E is a constant, right? At y equal a, y equals 0. What we know the electric field is, thank you then. We know that it's changing only at y. So it's actually, each one of them is a constant. So let's found it. So this one is actually equal to what? dy equal a, it's bigger than that. So it's this. So this one is equal. sigma 2 epsilon naught plus at the y direction dot dx dz, not y, also at the y direction, right? Right, and this one actually killing themselves in the same direction, and there's the integral, right? So if I'm gonna sum all the dx and the dz, it's actually, you know, it's from 0 to a, it's from 0 to a, it's actually a squared. So this is a squared sigma 2 epsilon 0, right? This was the roof, right? Plus, we have this contribution. And I'm gonna do this separation. So what is EY 0?
Negative sigma 2 epsilon.
We have negative sigma. Yes. Help me.
2 epsilon.
Yes. Y direction. Perfect.
Times d dz dx.
Dz dx at
Y. No, it's negative y.
perfect.
Yeah.
Negative y. Okay. So these two minuses actually killing each other out. So this one is a squared sigma 2 epsilon 0, right? By the way, this is a question for exam. This is a question for exam. Okay. Okay, so we're gonna sum this one and this one, and we have our final result. Right?
No way.
You ask for the charge.
Huh? Good. We didn't finish. Gauss's law, what Gauss's law said, cameraman? What Gauss's law said, if you found this thing, we can find this thing, right? So let's finish the question. We don't need the electric field anymore. Okay, we want this thing, so we know that this one is actually equal to a squared sigma divided by epsilon, right? Equal to q in a epsilon squared, cancel, found it. Yes?
Yeah.
Now I want to ask you a question. Did you care what was the what make the electric field? We didn't need it. We just wanted to know what is the electric field. So I'm gonna tell you that if you want to check it out, so if you're gonna do this thing we have here, let's do it the same way it was. If you're gonna have this is y, this is x, this is z, and we're gonna put here at the height a/2 charge of minus sigma, and we're gonna put here at a 3/4a another infinite plane with the charge plus 2 sigma. Okay, you're gonna actually get by superposition the electric field that was before. You were not aware what made the electric field. You just know that Gauss's law holds. Understand? If you know, I can make this question harder. I can give you this, find the electric field, fine, and then ask you what is the charge. But actually it was a really easy question because what you can do, you can draw the box, say how much charge you're actually taking, right? You understand? Sum it up, say Q total equal to what? To the whole charge. And you said that you have contribution to each plate, right? You have sigma dA upper plate, sigma dA lower plate, and you just found it. You would find Q in A. Okay? So equivalent question could go in that way. But without know what reducing the charge, you can come with a device, measuring the electric field. I don't know what's going on, and I can tell you what is the charge that we have in this area inside. Understand how strong tool it is in biology, in chemistry, okay? Finding medicines, do devices. Gauss's law is an amazing tool that makes stuff easy for us, okay? So what I encourage you to do is go to the homework, do as much as Gauss's as you can, get this tool, okay? Get it in your pocket, okay? Because we're gonna need it. Every time right now, we're gonna try to find electric field. Gauss gonna be our favorable decision, okay? Got it? Thank you very much, guys. Enjoy your weekend. Close the camera. Hope this lesson helped you.
Thank you.
And regards the homework, guys, regards the homework, I think that homework 2 was pretty fair. I know that the sphere and also the infinite wire was really complicated, but it was not complicated in the physics. Agreed? You had the tools to do them. A lot of students find it hard, and I want you to try, okay? This is the Definion. It's like the NBA for basketball player, okay? This is the NBA for engineers, okay? So we're expecting you to work hard and find it, okay? Thanks, guys.
Thank you.
Thank you. Yosef, you have a question?
No.
Perfect, okay. Say thank you to the guys here that help you. What is your name, remind me? Shubanger?
Thank you, Shub.
Shubanger saved your life.
Thank you, Shub, for recording this.
And YouTube viewers, Ben helped me with the camera.
Yeah, but Ben is the one job to be.
You always should compliment, okay? Always said his job was insane. It was good. It was never said that somebody is not doing it good. Tip for life. Yeah.
Now we should watch the tutorial before the potential or yeah. Yesterday we watched it first.
The honest answer was that I brought some demonstration and I want to teach you a potential, but we didn't get to it. I think we did so much today. Honestly, really honestly telling you that the Gauss, I think it's the hardest subject to capture, but it's the best subject to capture. And I saw your reaction and I said, fuck it, let's do another Gauss. Let's do Gauss, okay? And we're gonna meet on Monday to do potential. You know what? It's a little bit problematic. What's we're gonna do? Do you have extra time now to do potential, to take a break and do potential? You know, if you have class, you need to go to class.
People left.
What?
People left already. I'm okay.
Like, I'm fine with it. Like, I just need to get.
Let's take a break and meet at 12.
We have class at 2:30.
No, we're not going. We have a 20 minutes we need to complete. You need to see these 20 minutes before diving into the potential question.
Next week, Wednesday, maybe?
What?
Next week, Wednesday?
No.
People will know it.
What is the submission? You have Gauss this week?
Yeah.
Gauss is tomorrow.
Gauss is for tomorrow.
Potential of no
And so let's.
Potential is like 29th. It's from 7
Yeah.
days from now.
We should start potential.
You know that the time is actually managing us. We don't manage the time. It's important to understand this concept, okay?
I'm fine with doing potential right now.
I can have only one student, it's okay. If you're gonna deal with the camera,
But is it now, like, because
I want you to have the freedom, that's the idea. I want you to have the freedom to have enough time to do the homework, that's the whole idea.
how long are we gonna?
It's gonna be 20 minutes, potentially. I don't want you to miss the class, you have in 30 other class.
No, that's 2:30.
2:30.
2:30, so what is the problem?
It's different than us.
No, like it's fine. Like I can stay with.
I'm sorry, but I want to give you extra. That's the reason. Okay. Comment on YouTube. Some of you comment on YouTube and I answer. It's really good. Good questions.
You answered me the question and it was good.
What?
I asked the question and you answered
It's
me.
super easy and it saves us time.
I put the time like you asked.
I'm gonna make a tea. If somebody can stay in the class, watch the camera.
I was going to.
Okay, I'm waiting for you. You have a question? Sorry for waiting.
Yeah.
What? You go that way, you're gonna see to your left to go to the bedroom. But go down the stairs and look for the letter. I have a question about this big question from the homework. Yes, we have the big. Okay, press it. Are we playing the board in the meanwhile?
I'm gonna buy it. Okay. Planning to stay.
You know what's best? You know what's best? Wait, stop typing. You know what's best? All of the things gonna be on YouTube. And it's gonna be better if you're gonna comment to the specific time on the YouTube video, which you had a question. And then I'm gonna answer not you, but the rest of the people that are gonna take this class. This is fine for you. Copy that, exactly. Copy that and comment on the YouTube, okay? Then I can have also a break, drink something and do the next round. Is from the homework, not the homework that we did today, the sphere. You've been here when we did the sphere? You're talking about this question? We had, remember that? You're talking about that question. What is the electric field here? Okay. I have a question about the sphere question from homework. I don't remember the homework. We have the thick shell and the charge inside. Okay, perfect. Since the symmetry can create a big sphere that includes everything, it's a question about Gauss. Yes, definitely. Why not? It's a sphere, you have the symmetry of the sphere, and it's another sphere, you have the symmetry of the sphere. It sounds like a good idea to use Gauss. Okay?
It was literally in the Gauss homework question. Why didn't you think it was Gauss? I know, it wasn't the Gauss homework.
I'm gonna have a drink because I need my throat to Yes, follow me. I'm going to show you. Going to the same direction. Where is my mask? Where's my mask? Here.
Yeah. Toby, what are you doing? Don't touch it.
I'm planning to go.
Oh, the last question.
The insurance place, the insurance place. Violet.
She left.
Yeah.
So, where are you going?
Gonna buy her a cake. Present.
Ooh.
Wait. Stop. You stopped the recording?
No, it's still recording.
Huh?
It's still recording.
Here it is.